physics. What's a physical law? And he says, I think, something very deep, which is if you allow arbitrarily complicated laws, then the concept of a law becomes trivial or vacuous, as a pure mathematician would say, because there's always a law. So then he goes on to say that in his opinion, this means that the notion of a physical law, of a scientific law, really has implicit in it the notion of complexity of the law. Because they really, it's meaningless without the two things. Because you can't distinguish observations which follow a law, you don't know if you have a law or not, unless you have a notion of complexity. Because if you allow laws that are as complicated as your observation, very complicated, then there's always a law. And so this is meaningless. But he says the problem is how to define, it's not clear how to define this notion of the complexity of the law. If you take it to be the size of if the law is an equation and you take it to be the size of the equation, well, that depends on the mathematical notation at any given moment in the history of theoretical physics. And that's a time-dependent notion, which doesn't sound like it captures this deep concept of a law. And then Hermann Weyl goes on, since he's originally educated in the German-speaking world in Europe, before the Second World War, he goes on to say, this idea really goes back to Leibniz in 1686. And in 1686, in a work called the Discours de Métaphysique, Discourse on Metaphysics in English, 1686. So that was a big surprise for me, so I tried to learn a little bit about Leibniz. And if you go to this rather small document, the Discourse on Metaphysics, which is originally in French, in rather clear, straightforward French, if you look at paragraphs 5 and 6, you find the following idea, which is Leibniz is trying to distinguish a world which follows law from a lawless world. How to tell whether science is successful or not. This was 1686. Modern science was just beginning. It was then called mechanical philosophy. And I think at that point it was a legitimate question, since modern science had not yet destroyed all the opposition. It was a legitimate question to say, how can we tell the difference between a world where science can work and a world where science doesn't work? You know, how can you tell whether a physical system follows a law or not? What is a law? So Leibniz takes the following example. He says, take a sheet of paper, and you were using a sheet of paper to graph experimental data. Okay, so you have data points. But he says in his fantasy, you can just, what if you just take the graph, you get it by sprinkling ink from a quill pen onto the paper, so you'll get spots of ink, a finite set of spots, dots, points on the plane, on the graph paper. So now we can ask, do these points follow a law or not? And so Leibniz says, well, you might think that the way to define a law is to say it's a mathematical equation that passes through those points. And Leibniz says, but no, that doesn't work, because there's always a mathematical equation that passes through any finite set of points. So how can you tell the difference between points that are lawful and points for which there is no law? And typically, if you're going to scatter the points at random, there won't be any law. So Leibniz says, well, if the equation is complicated, then there is no law. But if the equation is simple, that's a law. And what Leibniz actually says in French is, he does say simple, which is simple, but he doesn't say complex. What he says is fort composé, which means highly composed, which is, I think, for him it's the opposite of simple, is fort composé. But it's translated, usually that document is translated into English as complex. But the actual French is fort composé, which I think is interesting. So this, Weyl says, is the original source of that idea of his, which is fundamental for distinguishing, at a philosophical level, for discussing whether science works, whether the universe is lawful or not, for distinguishing a world in which theoretical physics is possible from a world in which it's not possible. Okay, so this is the long history of these ideas. Now, if you look at the version of Leibniz and Hermann Weyl, they're talking about continuous mathematics. For them, the experimental data are points on a piece of graph paper. And for them, a potential theory is an equation. So you end up with trouble. It doesn't really work well that way. So the crucial point for me, this is the beginning of what I like to call algorithmic information theory, which is this notion of program size complexity, algorithmic information. And this is the central, for me, this was the starting point of my work on this when I was a teenager. And it also was for Ray Solomonoff. I and another one of the founders of algorithmic information theory, who is Kolmogorov, Kolmogorov and I were interested in defining randomness or lawlessness or lack of structure. Ray Solomonoff was interested in prediction, in a formal model of induction of the scientific method. So we're the three people who in the 1960s came up with these ideas. And one of the essential points from a mathematical point of view is your data are no longer points, and you're not using continuous mathematics. A theory is not an equation. Here, theories are algorithms, are programs. And here, everything is discrete. Your data is not continuous, it's not points on a plane, it's a finite sequence of zeros and ones. And your theory is also a finite sequence of zeros and ones. So it's very easy to know when the theory is good or not. It's very easy to compare the information in the theory with the information in the data and see if you have a real theory or not. So with changing in mathematics, usually the best way to solve a problem is to change the viewpoint. And then the problem becomes obvious how to solve the problem. So this is how to solve the problem, we think. So what can you do with this idea? Well, people have gone off in practical directions, but I think it's more interesting to look at this immediately leads to some mathematical questions, which I think are very fundamental. So I'm going to drop the physics now and head into metamathematics, okay, from this model. So in mathematics, you can also make a model of a software model like this one that I'm erasing of what a mathematical theory is. Here I've talked about what I think a physical theory is and how to measure its complexity, its information content, its conceptual complexity or information content. So we have that little model. Now we can make a new model, which has the computer again. And what do you have? Well, now it's a mathematical theory. So the theory in this case is going to consist of what? Well, your axioms, your mathematical axioms. This is Euclidean geometry, for example, or Peano-arithmetic, or Zermelo-Fraenkel set theory, whatever your set of axioms are. And out will come what? Well, will come out all your theorems. And there is this notion of a formal axiomatic theory, a completely formalized theory, a formal mathematical theory. And the idea of this, I think, was stated most clearly by Hilbert about a century ago, that a completely formal theory, this notion of an absolutely objective mathematical theory, there should be a proof-checking algorithm. There should be a mechanical procedure to check whether a proof is correct or not, whether it follows the laws. This is his notion that this should be objective, not subjective, so therefore there should be a mechanical procedure. In other words, an algorithm. So the notion of a formal math theory is that there is a computer program. You have a referee for checking a theorem, purported proof of a theorem, and it will either say the proof is correct, this theorem has been demonstrated, or it will say there's a mistake here. And this will be done via an algorithm. So if you have such a proof-checking algorithm, this may seem like a reasonable requirement for a formal mathematical theory. The way you get a theory like this is you have to put in all the missing details in the proof, and you have to use symbolic logic, mathematical logic, not normal language, which is ambiguous. So it looks sort of like a programming language. And the idea is that if you are very careful and you use symbolic logic and you take all your implicit assumptions and put them in as axioms, there should be an algorithm that can check if a proof is correct, if you've put in all the missing steps and you're using a formal language, mathematical logic, not natural language. So if this is the case, then it turns out, in fact, that there is a mechanical procedure or algorithm that will, in fact, produce all the theorems all the consequences of the axioms. This is an infinite set of theorems in any given mathematical theory. And the way it does it, basically it runs through all possible proofs and checks which ones are correct. And every time it found a proof that's correct, it's found one of the theorems. And you can systematically run through all possible proofs in size order. You know, look at all 1-character proofs, 2-character proofs, 3, 4, 5. The number, you know, your formal language has a finite alphabet, and therefore there are only a finite number of strings from that alphabet of any given size. It may be large, but it's finite. And you can just check each one and see if it's a valid proof, and if so, you know what it demonstrates, which is the end of the proof. And this way you can mechanically generate all the theorems. So the point of view, my point of view is that the complexity of a theory is an algorithm seen from a vast distance. I'm not interested in the axioms or the kind of symbolic logic you're using. I'm only interested in the fact that a theory is an algorithm which will generate all the theorems. It's a computer program for generating all the theorems. And the complexity of the theory is the number of bits in this computer program. Again, this is the algorithmic information content of your mathematical theory. And it's, roughly speaking, the number of bits of axioms in your mathematical structure. Okay? So it looks very much like the previous diagram, only this time it's applying to mathematics, not to physics. Okay? So what